Welcome. In this lecture, we are going to talk about adaptive on-time digital control for discontinuous conduction mode, and we want to show Verilog HDL based implementation. So, we will first talk about, we want to revisit the peak current based adaptive on-time control, then FPGA implementation aspect, Verilog HDL based programming, and finally hardware implementation and experimental results. So, if we take the adaptive on-time, this thing we have discussed in the previous lecture, and here we want to retain the same feature of constant on time, where the ripple voltage will be independent of load current, but it is still a function of input voltage, and we discussed in the last lecture also, if the input voltage increases, ripple will increase. So, we want to make sure the ripple will be more or less insensitive to input voltage also. So, if you replace here, we are not giving any timing constant from a timer, rather we are using a peak current based constant on time, and if you replace, and we have already discussed in lecture number 24 in detail, it can be shown that output voltage ripple will be independent of input voltage, and it is already independent of load current. So, this will retain all the good feature of constant on time. At the same time, it can be made insensitive of ripple can be made insensitive to input voltage. And now we are going to talk about the adaptive on time digital control, how to implement using FPGA. So, here what we are talking about? We are talking about this part, this is the current reference. So, I will say this is the current reference, it is coming from digital domain, and this is your DAC, this part is in analog, again this part is in digital. So, just to demarcate the analog part, we will use a different color, this part in analog. Okay. Now, that is why we want to implement this logic, and we have discussed that we need A to D converter for voltage comparison. In fact, in commercial product, we can simply use a analog comparator, no issue. That means, we want the output voltage how it is compared with the reference voltage, and when output voltage falls below Vref, then we will get QTR. So, in that case you may not need an A to D converter, and we will be discussing in the last lecture that some of this architecture can have purely analog implementation, and the other blocks timing circuit, digital data, they can be processed through digital, and that way you can reduce the cost. Here inside this block there will be a minimum on time adaptation modulator, and that require an enable block, minimum of time, then this clock will be used to count that all timing calculation will be done based on this high frequency clock. Then it will generate and Q out, and we will show how Q out can be mapped to high pulse. In DCM it can be straight away sent, no dead time circuit is needed, and then Q finish is the time when the on time adaptation, that means on time is elapsed followed by the minimum of time elapsed, then it is again it can accept another trigger pulse for on time if it is required. So, it consists of a main module which is called adaptive code PFM, then a clock generator circuit, adaptive on time modulator, and a clock manager. So, how does it work? And the clock manager inside there is another module is a edge detection circuit. So, if we go inside, so adaptive code PFM, this is the main module, the name of the module, and you can see the module name is coming here. So, that means this is the module name. Okay. So, this is the module name. Then any module which is the interface of this module, it has to communicate with the real world data, and we need to figure out, because this can only accept digital IO data. So, naturally there is an ADC. So, first of all, there is a high frequency clock which is here, then Q load which is going out, here we are not giving any load transient. So, we are disconnecting Q load, because we are not making any load transient, but when you go to multi mode we will show load transient. Then here Q low, this is your PWM Q low, then Q high is here, PWM high, and the analog comparator is here, you can see this is a comparator hawk. Then you also have a clock data, actually that will be here, a DAC clock. So, which will be coming to this clock is here, clock DAC. Okay. Then there is a clock ADC which is here, clock ADC. The clock ADC is here. Clock ADC is here. Then ADC data. So, where is the ADC data? If we take another, so this is the data. This is data, vector data. This is coming here, ADC data, and the DAC data which is here. You can see this data is here. Sorry, DAC data. So, maybe I can use green color. So, this is the DAC data. Half part is going here and here is a continuation. So, that means we have interface all this real world signal, that is why it is the main module. And we have also discussed it require an UCF file, user consent file or the implementation file, and that I am not going to show because we have already discussed the procedure of running UCF file and so on. We want to synthesize the internal module which will be prototype using FPGA. So, we have to declare which are the input output, and from this picture it is clear, from the direction it is clear which is going out, which is coming out, that is the output, which is going in, that is the in. And input also we have a vector data, that is the ADC data sign, and the output, though this is in Q1.9 format, and this is the 12-bit offset binary. We have discussed already, our ADC is offset, our DAC accept offset binary data. Then, sorry, this is offset binary. Then here we are setting a peak current reference which is equivalent to 2, but we later found it is 1.2 ampere. It is roughly around 1.2 ampere. Yeah, closely, I mean it can vary just because there are some other delays and all. So, the target is 1.2 ampere. Then we have a reference nominal voltage which is set to 1 volt, but if we, and we also set a timer which will generate the minimum of time. That means, what is the minimum of time? Because it is a constant on time modulator, so it also have a minimum of time. And here we are setting 26 into 10 nanosecond, 260 nanosecond, or it is 0.26 microsecond. That is your T of T mean, which is the minimum of time for this constant on time. Now, we are defining here the reference voltage. We are using a muxing because you can make a load transient, but here we are simply taking the reference voltage to be the nominal value. Okay. This is one which is your research comparator. That means, you see that at the clock edge, yeah. So, this is another issue because we face some difficulty here. If we take the directly comparator output, if you go to the main module, this comparator output was used in multiple places inside this block. So, it was getting loaded. That means, if you take that signal and this is a IO pin, it may not have sufficient current driving capability, and if you use that pin to derive multiple circuit using that pin, then this pin may not have sufficient current to drive, because if you use just comparator 1 or 2 block to trigger, that is fine, but this comp will be using multiple time inside. So, there are two possibilities. We can put a buffer circuit, additional buffer circuit, or here we have used a clock synchronized comparator. That means, if we have an analog comparator, we are actually that analog comparator, let us say this is comparing with peak current with V sense, and you can see it is minus and plus. This is analog comparator. This will be our comp. Now, this comp we are using like a D flip flop, and this is our clock, and this is our high frequency clock, and this is Q. That means, the output will be comp, Q output will be comp, which is the reset time. So, here we are using reset time. This will be reset time only when the clock edge come. That means, it will go inside this block whenever the clock edge come, otherwise it will not take. And since the frequency is very high, that means this is a very high frequency clock, this clock. So, if the comp changes, let us say the comp changes somewhere here. Okay, so let me draw how does it matter? So, suppose if I draw a timing diagram like this, this is the timing diagram. So, let us say we have this high frequency clock. So, this is our high frequency clock. So, this is our FCLK and this is our comp, which is a comparator output. Let us say comparator output goes high, somewhere here, it goes high somewhere here. So, we cannot turn on immediately. So, we have to wait for this clock is to come. That means, whatever you are using RST comp, that means reset comp, or basically clock, RST temp, the name here, whatever signal we are using here, this one, that means RST temp, some name is given. If you draw this particular clock, that means if you continue, it will be turned on. When it will be turned on? It will be turned on here. So, that means there is a delay, and this delay maximum can be up to T clock, because there is a time period. So, this is basically a comparator operation, but with a clock synchronized. So, this due to this delay, because it is a clock synchronized comparator, I would say it is a clock synchronized comparator. So, due to this delay, sometime your peak current can exceed the reference voltage, because you are not turning off the switch, rather due to this clock synchronized operation, you are taking action after some time. So, this may be possibility. So, it may exceed the actual constant on time, but there are n number of ways to tackle this and solve this buffer problem, but I am not going to discuss this because it depends on the user. Then we are calling one is the clock generator block, and this we have discussed, though we are not using DAC clock, but it is still there. This is a highest resolution clock, and this was a switching frequency clock which we have used for PWM. And this clock, the frequency we are taking like like a 200 kilohertz. That means after that means what is the time period? It is 5 microseconds. That means after 5 microseconds, this edge will come and it will check whether your QTR is high or low. If the QTR is high and monoshot timer is still not activated, it will simply turn on. Okay? So, that is why the external signal. Adaptive on-time modulator, it requires an enable signal, because we have discussed adaptive on-time inside, it requires enable, and it also requires a reset, that is the comparator output, which is a clock synchronized in this case, and the high frequency clock is used to generate the minimum of time using this timer. And then the Q out, which is the output, and this output consists of the on time followed by the minimum of time, and then this Q finish will be enabled. That means, if an edge come, which is, let us say, I would say that if the enable signal goes high here, if a edge come, then what will happen? Your constant on time will be activated. Okay. So, this is our T on, which will be coming from the current loop, and there will be minimum of time. That means, this is the time which will be T minimum time. It will not be on even though any pulse come, because it has a minimum of time. Then it will check here. So, here your actually our Q finish, that means whatever clock we are talking about, it is basically this clock. So, whenever this minimum of time, that timing is elapsed, it will generate this, and because this is to check whether your QTR is still high, that means whether your output voltage is still below the VREF, then it may trigger another on time. And then this is the clock manager who will generate this enable clock, and we are going to discuss. So, the clock generation block we have discussed multiple times. So, I am not going to discuss. This is to generate switching frequency clock as well as the ADC clock, and we have discussed lecture number 74, 75 in the context of voltage mode control. The same module is used. Now, adaptive on-time modulator, here we have already discussed in the previous lecture. That means, we have this peak current reference here, which is coming from the DAC, analog current reference, and this is analog comparator and the sense current. Then this will actually create a reset pulse, and this is coming inside, and that means this comparator output is there, and this will be one of the it is a reset pulse to turn off the monoshot timer. And how, what is the module? So, this module accept the enable pulse, that is the trigger pulse, reset, which is nothing but this reset, that is the comparator output, but here we are using clock synchronized comparator. Then F clock, this is needed to generate this for the free running counter high frequency clock, and this is a minimum quantity, it will generate the reset pulse, which will enable, because we discussed that if the on site timer is on, then it will be minimum on time. So, this duration to generate, this is the circuit, the whole circuit. This thing we have discussed in detail. Then this register, then if you this is our this particular block, if you see this block is this always block. So, it will check at every edge of enable as well as the reset, whichever comes this line will be executed, this whole portion will be executed. So, it will first check whether reset is high, then the output will be, this output will be 0. So, this output will be here, and these are the two output, right. But if the reset is low, because it can only enter if the enable edge come or the reset edge come. If reset edge come, it will see reset high, it will be 0. If the enable edge come, and that time if the reset is 0, then it will take 1. So, that is why if the reset is 0 and if the enable edge come multiple time, this will remain at 1. So, it will not change the status as long as the reset come, and this is a reset dominated pulse, because if the reset come, then nothing can happen, it has to reset. Okay. Now, this is the next one, which will be this one. So, this is here, you see it has two input pulse, reset and reset 1. This is the reset of this pulse, and this is reset 1 for this pulse. Now, again in this case the reset 1 is dominated. If the reset 1 is high, this output will be 0. If this is 1, it will be 1. And we are making a NOT operation of this, so that making sure whenever this guy is basically 0, then this will be 1. So, this will pass that on. When this guy is when this guy is 1, this will be 0, this will be 0. So, it will make, because there is a NOT operation here, just a minute, reset, okay. So, this is the combination of Q1 and Q2, yes, because when this is already high, then this will not start, this will start at this edge. So, that means this is our this particular Q temp, let us say, and what will be this? This will be high for this time, this is this pulse. Okay. So, maybe I can use a different color, this is this pulse, this is the minimum of time. So, during this time when this is high, then this will be low and this will be whatever is the signal, it is the AND, so it will become low. So, that means the net output will be, if we take the net output, this will high, this will be low, and again now this is released. Now, you can turn on again if it is required, but till this time it cannot turn on, there is a minimum of time. Okay, and this logic is enable and disable. Clock edge, it will check. So, this is this particular block, it is implemented here. Okay. So, you can say whenever this is low, the reset, that means if this is high, then only the counter will be incrementing. If it is low, then the counter. So, if this is high, then this will be low, the reset will be deactivated. If this is high, the reset will be deactivated, because it is a active high reset signal. So, if it is high, then this will be 0. So, this will be 0. If it is 1, then this will be 0. So, reset is disabled and it will start count, it will count. But when this is 0, let us say this is 0, in that case this will be 1 and then reset will be activated, and as a result in the circuit will be disabled completely. Okay. So, this is the, and this Q finish is coming when your off time, minimum off time is over. The clock manager will simply take QTR. What is QTR? We have discussed that we have ADC, this is your feedback voltage and this is your ADC data. This is compared with our NREF. our N ref, and if it is less than equal to high, so this is your QTR, and this QTR is coming from here, and this signal is used here also multiple times. And this all, if QTR is high, then whenever QTR becomes high, that is required to turn on the monoshot timer. Or if it is high but no edge is coming, then it will check the minimum on F minimum will come, that will come from a edge detection circuit, and you see the minimum, because we will pass the QTR, detect that this. So Q min, what is Q min? It is the combination of QTR and F min. And how do you generate F min? That we have discussed in the, if you go to this block. So F min will be the main when you module instantiated. Yeah. So F min, if you see F min, it is the QF. That means when this monoshot timer on time is over and off time is, minimum off time is over, then this QF will be enabled. So that means this F min corresponds to the flag which shows that minimum on time is elapsed, and if that time QTR is high, it will generate the enable trigger. So enable trigger is a OR combination of all these trigger pulse, and it can come multiple times. When the switch is already on, it will not change the status, but even these pulses come during minimum of time, it cannot turn on the counter. Okay. So the module of the edge detection, it is simple. Edge detection, what we are doing, whatever signal we are getting, we are talking about the positive edge detection. So we are delaying by another signal. So this is the your, let's say, one particular signal Q, this is Q delayed, and if we do XOR, that means Q and Q delayed, sorry, if we do Q and Q delayed, if we do XOR of this, then this will be high, and that is ANDed with this particular signal, that is your Q, and this is your positive edge, pauses of Q. Okay. So this is a circuit, and here we are making 2 unit delay because there is a blocking statement, 2 unit delay, because it depends on the F clock, which is a high frequency clock, 10 nanosecond. So we are making a 20 nanosecond delay. Then adaptive, again this is the logic I told you, this will generate comparator status, which is our QTR. That means we name here comparator status, that is our actually equivalent to what we are using QTR. Okay. Because if you go back to the main module where we are instantiated, you see the QTR is nothing but comparator status. Okay. So that means we have discussed in detail, and the DAC, since it accepts the offset binary, we have defined I peak in 2s complement. We have to simply invert the MSB, and that will convert any 2s complement into offset binary. So that is going to the DAC, and this is a hardware implementation detail. So you are using our buck converter in DCM mode, and we have already discussed that our power stage, inductor, capacitor, input voltage we can change, output voltage also we can change, and since this is an adaptive on time, the switching frequency is varying, and we are using a low load condition, the load resistance is high, 13.5 ohm, and this is adaptive on time experimental result. Other detail, we are using 10-bit ADC, controller clock is 100 MHz, and we are using a current difference of nearly 1.2 ampere. Again, this can slightly vary because peak can slightly be higher because of the delay. And experimental condition, if we use, we are varying input voltage, and what we want to expect, we know that output voltage voltage ripple or will be more or less, I would say, it is independent of input voltage variation, delta V, I will say. I will not say it is totally the variation in the input voltage. So this is the condition where you are operating at a higher input voltage, and you can see the current division is 0.5 ampere. So this division is 0.5 ampere. So we are getting here the peak current reference of around roughly 1.2 ampere. Okay, and you can see the voltage ripple here because in the DC couple mode. Now we have reduced input voltage from 3.3 to 2.5. And what you will find, the peak current reference remains same, more or less same, 1.2. As a result, the output voltage ripple also can be shown to be same, because you can see the ripple voltage has no as such effect. Another interesting fact, because we know that the time period, effective time period between two consecutive on pulses is actually the frequency, it is related to the frequency of PFM. But here it will not be perfectly stable, because we are not using an analog comparator, we are using an ADC, which is we are using a 20 megahertz clock, that is there is a 40 nanosecond, every 40 nanosecond the data will be available. As a result, we have a time resolution which is 40 nanosecond. In case of analog, we have infinite time resolution. So, this can cause some deviation in T effective in the subsequent cycle, and that we have discussed. But on an average, if you see T effective for both the cases, since the load current is same, the frequency does not depend on the input voltage in this case. That means, your switching frequency will be linearly proportional to load current. Here it is almost independent of input voltage, because we are using adaptive on time. The time period will be more or less maintained. And if you go to the other, that means 2 volt, that means we are decreasing from 3.3 to 2, we are maintaining the same peak current, and the voltage ripple is also sort of maintained, but the time period. So, in all cases, if you T effective, I will say average value if you take, because there is a resolution due to the 40 nanosecond difference, and if you take T effective average case 1, case 2 and T effective average, I would say case 3, all will be more or less equal, and that is the beauty. That means your effective switching frequency, I would say effective switching frequency is almost constant in the average sense. So, it is insensitive to input voltage variation. Generally what happen, if you remember the formulation in on time, if you keep the input output voltage constant, then the frequency varies with load current, but if the load current is fixed, frequency will be fixed. But there we saw, if the input voltage increases, then naturally because on time is fixed, the ripple will increase, and as a result time period will increase and the frequency will decrease. That means, in traditional, I will say traditional chord constant on time, the frequency will be inversely proportional to input voltage. That means, if the input voltage increases, the frequency will actually frequency will decrease, because the time period will increase. But here in this adaptive on time, it is more or less constant. So, it retains good feature, that is why many commercial products use this peak current based adaptive on time control. So, in summary, we have discussed peak current based architecture, their FPGA implementation aspect. We have also discussed Verilog HDL programming of this adaptive on time digital control, and we have shown hardware implementation as well as experimental results. That is it for today. Thank you very much.